Okay, so today we arrive at a very nice topic of sampling. It's a very important topic and one of the highlights of what you learn in this course, in my opinion. And now that we have all this understanding of the Fourier transform, we should be able to go right into it and understand how to sample a signal into discrete time in such a way where we can recover the signal, which let's discuss what we're talking about here. So sampling is the topic. Okay, so imagine that you have some continuous time signal and it goes into some system that call this an analog to digital converter. And what comes out is a digital signal. Then perhaps we process that somehow. I'll represent as a block diagram. We process this digitally. We can use FFTs. We can do all the stuff you do in MATLAB. And then still digital, let's say. And then we stick it through another device that turns it into an analog signal again. Analog, whoops. Yes, okay. A digital to analog converter. And out comes a continuous time signal. So this is a common design for digital signal processing, for example. So let's say. And you can actually buy chips that have all these components on them. You can buy cards for a computer that have these components. They will do the sampling and then allow you to program in some digital processing, and then they'll turn it back to a continuous time signal. Now, this digital signal, what we mean by that are a couple of things. One is that it's discrete time. And also, it's quantized. Okay, so what that it's quantized because even though changing it from continuous time to discrete time seems helpful in terms of storing such a signal in memory, you still can't actually save arbitrary numbers into memory. You have to represent them in bits somehow, at least for digital memory, and so you have a finite number of possible numbers you can use in your set there. Okay, we are going to focus on this, the effect of taking your continuous time signal to discrete time. We're not going to worry about the quantization for now. We will talk about that in a few weeks, maybe next week. But right now, we can just imagine that we are actually saving exact numerical values of the signal. In a lot of signals and systems courses that are offered to undergrads, this is completely ignored for the entire conversation, although I think we will get a chance to look at quantization in some detail in this course. Okay. So you can think about this first part, sampling, as the following. Let's say here's some continuous time signal. And you have some sort of clock signal. So this is your continuous time signal. And you have some sort of clock in your system that just consists of some square wave. That's just going like this. Actually, I'll say 0 to 1 values. And this just tells your analog to digital converter, this controls the circuitry in the analog to digital converter, and perhaps every time this goes up, the circuitry takes a sample and basically saves the value into memory at that moment in time. All right, again, this goes up, and that tells it to save here, save this number, so forth. Okay, so you can build some circuitry that will do something like this and save those numbers. Okay. Now this isn't, and so the output then is just a sequence of numbers, which we can think of as a discrete time signal. And this is what gets saved. All right, so there's your discrete time signal. And of course, we have a sampling frequency, right? So if that was t, then we would say sampling frequency Fs equals 1 over t. Let's say Ts. Okay. Now, there are other ways to build samplers, and some of them might have different consequences. For example, you can build a sampling system that doesn't just save the exact value at a given moment in time, but instead integrates over a short period of time and saves the result of the integral. So that's another way to build a sampler. We won't worry about all the possible ways you might sample a signal. We'll usually assume it's done this way, okay, when we say we sample a signal. But there are reasons, why it may be interesting to build it a different way, usually just for convenience of circuitry. Okay, so the question is, now that we have the digital signal, forget about processing for now. Let's just, assume that this isn't here and see what can we even get back the continuous time signal. So, so you can think about several ways of trying to do that. Any ideas? You have these red points here. What might you try to do if now you need to create a continuous time signal? Yes? Use the Fourier series of this. So how's the Fourier series? Oh, I see. Okay, wait. So the Fourier series of a continuous time signal we could use that to reconstruct a continuous time signal. Now, this is discrete time, so if you do the Fourier series, it's going to be periodic. How are you going to use that to get back a continuous time signal? So you're saying just use the reconstruction. You're very close. You could do something like this. Although if you just tried, what's going to happen is, because it's discrete time, the Fourier series is going to be periodic. Now, if you try to then reconstruct a continuous time signal from that Fourier series, the continuous time synthesis equation says to sum over all Fourier series coefficients. You're going to end up summing over, this sum won't converge. Okay, but we'll see that you're close to figuring out a way. What? Just sum over one period? Okay. You guys you're basically going to derive this. You're exactly on the right path. Let's talk about what might you do if you didn't know the Fourier series or the Fourier transform? Okay, you could connect them. So let me redraw my points here. So let's do this. All right. Here are our points. Okay, you could do a, what I heard here is you could connect them like linearly, like straight lines. Okay, that's one way. You could do, let me do something even worse, but maybe the first idea is just do a flat, make it flat at that value for the duration of the interval. Okay. So these are, there are names for these methods, and of course it's now continuous time. Okay, so this blue curve we call zero order hold. Now it doesn't look like a very great attempt at reconstructing a continuous time signal, although it's perhaps the easiest to build. You know, you have some output that just holds a certain voltage or whatever your output signal is until the next clock cycle where it updates to the new output. Okay, and maybe the easiest thing to build in circuitry is zero order hold. But let's say that the green then is a first order hold. I believe. And okay, it looks a little better. At least you get something continuous out. Still, though, you probably aren't going to believe that that green curve is actually what you sampled. Okay. There are some cases where you would know this is what you sampled. Let's just write those down. If you knew that x of t was piecewise constant, at the sampling frequency with 1 over Ts, then of course zero order hold gets you back your signal, right? Okay, and a very similar thing is if you knew that x of t was continuous and piecewise linear. All right. Again with 1 over Ts. Then first order hold. Okay, so these are kind of, contrived examples. This is just, assuming what you want about your signal that makes it exactly fit your method of recovering x of t. So if we knew that you were looking only at signals that only changed at given point. That if you knew it was continuous, well, I guess there's up to a shift of 1 over t. If you knew you were sampling at the corner. Yeah, so I see what you're saying. What if your samples were here, and then you try to recover the straight line? You're right. So you'd actually have to put not just the width, but that you actually sample it the way it's going. I could put that here. Okay, my point of this is actually just to make you notice that if we have certain assumptions about the signal, then we may be able to recover exactly, okay, just from its samples. What if we have no assumptions about the signal, any arbitrary signal, and we take samples? Is it possible to recover? No, it's definitely not possible to recover because you don't know at all what happened in between the samples. So I'm going to write here only possible to recover x of t with assumptions. However, we're going to find that there's a natural assumption that we'll be very willing to make that allows us to recover many signals. Okay. Oh, yeah, before we get to that, okay, yeah, let's do something else. Okay, we're going to do a brief change of topics that'll all wrap in. Continuous time, discrete time. Okay, I've mentioned several times that even though we have 4 different flavors of Fourier, we have Fourier series in discrete time continuous time, Fourier transform in discrete time continuous time, that they're also interrelated, that the continuous time Fourier transform can encompass all of them. And now I'm going to show more concretely why is the continuous time Fourier transform good enough to give us all our results. And the first step in that is saying that discrete time signals can be represented in continuous time. So let's give a natural way to represent them. Suppose xn is discrete time. Okay, we'll represent this with something we'll call x tilde. X tilde of t in continuous time. And here's how we'll define x tilde of t. It equals the sum n equals negative infinity to infinity xn delta of t minus n capital T. Where t is the sample frequency, sample interval. So we'll say, okay, so 1 over this t is what we're going to refer to as the sample frequency. Okay, so what have we done? We had some, in discrete time, we had some signal. Here was, let's say, something like that. In discrete time, this was xn. And in continuous time, we're just representing that as delta functions. And so this was, let's say, x minus 1, x 0, x1, x2, and so that was minus 1, 0, 1, 2. And in continuous time, we're just putting the amplitude of the delta function, setting that equal to that value. So this is just, again, x minus 1, x 0, 1, x 2. So that's what that definition gives us. Oh, and let's plot the horizontal axis. So this is at 0, that's at minus t, that's at t, that's at 2t. So this here is x tilde of t. So you see this is just a way we're going to choose to represent a discrete time signal at continuous time. This is the most natural way to do it. You can convert it back and forth if you have a signal in continuous time made only of delta functions at uniformly spaced intervals, then you could represent that in discrete time if you wanted. Okay. So let's look at how these two signals relate under their respective Fourier transforms. Okay. Okay, so let's look at x of f. I'll do that in blue. So x of f, this is discrete time. And we know that it equals the integral, oh no, sum, because it's discrete time. Okay, that's the definition of it. We also know it's going to be some periodic thing. Now let's do continuous time. X tilde of f equals the integral from negative infinity to infinity, tilde t. And let's plug in our definition. Notice up here we have the definition for x tilde. So that is going to equal put in that definition there. And then we'll finish off the integral part. Okay, so as you noticed, I just plugged in that definition for x tilde. But now we will switch the order of the sum and the integral. So notice that x of n is not a function of t, so it doesn't need to remain in the integral either, because it's constant with respect to t. Okay, now I want to focus on this part first. We have a shifting property for the delta function. Says that this integral, the limits are negative infinity to infinity, so I'm always within the limits, is equal to this function evaluated at the point t equals n cap t. Plug that in, e to the minus I 2 pi f, and then instead of t, we'll put n capital T, like that, okay, which equals x, I'm just referring now to that blue equation up there, that equals x evaluated at ft, and I find it better to think about this as equals x of f over, let's say, f naught, where f naught equals 1 over t. Okay, so in other words, the Fourier transforms are the same, except that we had one thing arbitrary, and that was what do we choose the time scale for a continuous time signal. We got to arbitrarily choose an interval here, t. So of course that's going to affect the continuous time Fourier transform in a very simple way. It's just going to be the continuous time Fourier transform is the discrete time Fourier transform with the scaling of 1 over f naught, this frequency that we used for the conversion. Okay, so that's nice. That at least makes us feel comfortable that this way of representing discrete time signals in continuous time keeps the meaning of the signal. If we weren't already convinced that it was so natural. Okay. It also tells you something. What do we know about the, if we have a signal like x tilde up there, what do we know about the Fourier transform of it, the continuous time Fourier transform? As far as period, is it periodic? So this is the Fourier transform of our x tilde. So suppose you have some continuous time signal made only of delta functions, like right here, evenly spaced out. Then we know that the Fourier transform is going to also be periodic, and what will the period be? It would be, the period of this is 1. This is always period 1. So the period of x tilde, which equals this, is going to be f naught. Okay, because we rescaled. So it's a period 1, but rescaled, so it's a period f naught. 1 over that t. I'll write that here. Okay. I want to, before we go on, just point out one subtlety. You don't, it's not crucial to recognize this, but I mean, it could lead to misunderstanding if you don't recognize it. Okay, this is about time scaling. If we define in discrete time, let's say this is discrete time, as we did in one of your problem sets, what if we define a sort of scaling operation that's like this, x sub k of n equals x of n over k when n is divisible by k. Zero else. So this just spreads our signal out with zeros in between. So we only have non-zero values every k. Right? We looked at this and we looked at what does this do to the Fourier transform and all that stuff in the problem set. Now, this is very similar to the following discrete time operation. X of t over whatever that number is, k. All right, that would spread out if k is positive. Here I'm saying, I guess, for k, an integer. We're only looking at integer k in that case. All right, so these both do very similar things, right? But they're slightly different when it comes to a discrete time representation. Here's what I mean. Green. Okay, what do I mean by that? I mean, suppose we take a discrete time signal. Let's take x. Let's look at what happens if we do xk of n, and we transform that to through continuous time. Okay, now I'm using this operation as if we do our continuous time representation of xkn, and we come up with something that we call x tilde kt. Okay, and let's compare that to what would happen if we took x. Okay, compare that to x tilde of t over k. So in this case over here, we did the time scale in discrete time. And here we did time scaling in continuous time. So basically, we're trying to arrive at ultimately something, the same thing. What we've done here is we started with a signal x. We've inserted a bunch of zeros to spread this out in time, and then we represent that in continuous time. And I want to see whether we get the same thing if we start with xn, first convert it to discrete time, and then scale it out, okay, by the same amount. Do you believe that these are the same? So let's vote each way. Who believes that they are the same? Raise your hand. Okay, we have a few hands. Who thinks they are not the same? A few more towards not the same. Any explanation? Does someone want to offer up an explanation why they are or are not? Use intuition. Oh, what is that? I'm sorry. Bulb went out? I hope not. What? Yeah, actually, I'm trying to think the bulb did go out because it's just completely off. Huh. Okay, that's too bad. I will use the board, but then I won't have notes to distribute to you guys. Okay. So. All right. Okay, any explanation why they would be the same or different? Yeah. So the fact that they're actually different, but in very subtle way. I mean, you'll see that they're different, but they're very similar. Okay, so watch this. Okay, let's look at xk of. First of all, let's look at what x tilde k of t is. Okay, by our definition of this transition from discrete time to continuous time, it's going to be a sum for n equals negative infinity to infinity of x tilde of xk n delta t minus delta t minus n at t. Okay, which is going to equal. Now we know this is 0 except at integer multiples of k. So I'm going to let m equal let n equal mk. where n's integers, and this is just the sum over n.
You write a little bigger.
Yeah. Okay. Sorry about that. I will write it all bigger. All right. All right, let's try this though. Xk of t, so we're doing tilde. Okay, that's the sum here of n equals negative infinity to infinity of x tilde of n of k. Sorry, no tilde. Xk of n delta of t minus n t. Okay, is this big enough? I know it's like the color is a little hard to read, but okay. So this is what we defined as taking a discrete time signal and turning it to continuous time, and then now if we use the simplification that okay, this equals the sum for n equals negative infinity to infinity of x of n, x of n. So what I've done here is I've let n equal n mk. This is the substitution I made, and I realized that as long as I sum over all integer values of n, I am going to include every non-zero term in this sum. Okay, so I only have to sum over n's instead of all the n's. And I should then plug in here, basically I can, let me put one step in between, and that is that I can keep this here and just do an m over an mk. Yeah. mk. Here. Just replace every n with mk. Delta of t minus mk t. Okay. And so all this step only involves realizing that if now I'm not summing over all terms, but it's okay, I'm summing over all non-zero terms. Right. And then that's the same as the sum. Now we'll just replace that definition. N equals negative infinity to infinity of x m. So I remove the subscript and I remove the k there by the definition. But I'll leave this one the same. T minus m kt. Okay, so it's the same as if I just took my discrete time signal and represented it in continuous time, but instead of using t, I use kt, and that's exactly what you're describing, I think. So you do the spreading in discrete time, and then you change to continuous time. It's exactly like you just took your original signal and represented it using a sampling of kt rather than t. But let's look at what happens the other way, and that is, and here what we want is x of x tilde of t over k. Okay, so we're doing spreading in continuous time. All right, so that equals, well, we know what x tilde equals, and then we'll just plug in the t over k to what we already wrote down for x tilde. So x tilde equals this, and equals infinity x of n. And then delta, and here we do t, instead of t, we should put t over k. T over k minus nt. Okay, so this is just, I just took the definition of x tilde, but I just plugged in a t over k. Now, what we need to do is use our we need to realize that this is the same, this delta function here. Okay, we can rewrite it as another delta function using our property of time scaling of delta functions. all right? Remember that if you scale a delta function, you affect the amplitude of it, okay? So recall this thing here, that delta of AT equals 1 over A delta of T. Okay. So what we can do here is write this delta function as delta T minus, let me do this, NKT over K. Haven't changed anything yet. I just manipulated the argument a little bit. And then I use this time scaling property to realize that this is actually equals K delta of T minus N. Okay, so in continuous time, when I did the scaling, now I meant these lines mean that this equals this equals this. Now notice if I plug this substitution back up here, then I get almost the same thing. So what I found is the conclusion is that the conclusion here is x tilde of T over K equals K x tilde K. So they're almost the same, but they're scaled. Okay, by the way, you might remember that when you proved properties of the Fourier transform, that time scaling property in continuous time had a 1 over A factor out front. But the time scaling in discrete time didn't. Okay, and I pointed that out in the problem set. It didn't, and the reason was subtle. Well, this is really the reason. It's the same reason you don't get, you get a scaling factor when you spread it out in continuous time and you don't in discrete time. Okay, so it's kind of subtle. That when you scale delta functions, you have to realize that affects their amplitude. That affects them under the integral. Any questions about this? Yeah?
Is there a reason we dropped that proof sign?
Just because I was assuming K was positive. Sure. Yeah, I could put it. Any other questions about this? Yeah. Oh, because we defined x sub k of n to be 0 whenever n is not divisible by k. Okay, so 0 whenever n is not divisible by k. I mean, this sum, in terms of this sum, will be 0 anywhere except when this holds for an integer n. So we can just sum over the n. All right, so enough about that. So now we know how to represent a discrete time signal in continuous time. The next thing we're going to talk about is I might have just enough talk to get through the question. All right, the next thing is representing the Fourier series as a Fourier transform. Fourier transform. Here's what I mean. Fourier series is designed for periodic signals or finite series signals. Okay. So suppose x of t has period capital T. And let's say that the Fourier series coefficient A sub k. Okay, then I claim that we could handle this under the Fourier transform narrative. Technically, before we knew about the delta function, we couldn't. If you take a periodic signal and you try to apply the Fourier transform integral to it, it's not going to do it. But because we have these delta functions, we now can actually handle this Fourier series in the Fourier transform domain. So what I mean by that is then for the Fourier, so Fourier transform here, following x of f. Remember, for the Fourier transform, it's not a sequence of coefficients, it's a function of f. But we're going to say that that just equals the sum k equals negative infinity to infinity ak delta f minus k f. Okay. Where f naught equals 1 over 2. All right. So this is very similar. This is just like we were doing to represent discrete time and continuous time. Now I'm claiming that actually this is the Fourier transform associated with that Fourier series. Okay. And I'm going to prove it. Prove that here. I'll prove it using the inverse of the Fourier series, and the inverse of the Fourier transform is show that they both get x back. All right. So the Fourier series synthesis the following: x of t equals the sum k equals negative infinity to infinity of ak e to the, oh, I'm getting small, sorry. I'll expand, I'll get it. E to the I 2 pi k over t t. Okay, that's the synthesis expression for the Fourier series. Now, okay, great. Now let's do the inverse Fourier transform of what I'm claiming is the Fourier transform. Xf. We'll see if we get the same thing back. Okay, so that says that x of t equals the inverse Fourier transform is the following. X of f, this is discrete time here. We know it's discrete time because I'm integrating from negative infinity to infinity. The same exact proof is going to hold in discrete time. So I'll do it for continuous time. So you can do the same thing in discrete time. Okay. This times e to the I 2 pi f t df. All right, and then now let's plug in what I claimed was the Fourier transform, this thing. So that equals the integral negative infinity to infinity of plug that in, sum k equals negative infinity to infinity ak delta f minus f naught. Okay, I just plug that in here. And then e to the I 2 pi f t t. And you know what I'm going to do next? I'm going to switch the order of the integral and the sum. K infinity, and the AK's come out, but they're not functions of t. Integral from negative infinity to infinity of t. Now let's look at this part here, and we use sifting property. We're going to replace df. Yep. Good point. And we're going to replace each f with a k F naught. And that's going to equal sum k equals negative infinity to infinity, ak e to the I 2 pi k F naught t. And now let's check. Did we get the same thing back each way we did it? Well, okay, you have to read in the shadow. So this equals this. Yes, it does, because our definition of F naught was 1 over t. Right? So these are equal. Okay, so if we want to take a Fourier series and instead call it a Fourier transform, we do this representation of the Fourier series coefficients in frequency domain. We've talked about this before. We didn't write it so explicitly, but we've talked about like thinking of the Fourier series coefficients in the frequency domain. And here we're just saying, fine, we don't need the Fourier series anymore. We can always talk about the Fourier transform. We'll just need delta functions in the frequency domain. Okay, and we don't need discrete time anymore. We can always talk about continuous time using delta functions for discrete time. All right. So that means that if you understand everything about the continuous time Fourier transform, then you understand everything about any of the Fourier flavors. Okay. Let me, okay, so the next thing, I'm just going to erase this. All right, so now I want to convince you that actually might run out of chalk. Does anyone have chalk? Okay, so there's a look at some, well, one in particular, Fourier transform. Let's say self-similar Fourier transform. One in particular I want to point out, although there's another famous one. Well, I'll put it here, but I won't get the scaling correct. You can look it up in the table. Here's one. What I mean by this is a signal in time that when you take the Fourier transform, you get the same thing, or at least up to scaling. The very first problem set I asked for as a bonus problem. What is the eigenfunction of the Fourier transform? And that's the exact same question. Saying, what kind of function could you apply the Fourier transform to and get the same thing back? Any ideas about this? Does anyone know of any signals that have the same, where the Fourier transform looks the same? Yeah? Great. So this is a nice one. This signal like this, all right, that looks like the following: e to the minus x squared, t squared. And now you could scale it with a constant, you could scale time, and so forth. So there's a lot of flexibility here, but it looks roughly like this. All right. And when you take the Fourier transform, you actually get the same thing. Now, again, I'm being a little bit careless about this because, so you get something like e to the minus f squared. Because I don't remember exactly, there may be a constant here or here, either in time or in amplitude, to make this actually negative. So I'll say, this may be incorrect as it is. In fact, if someone on the computer looks up the Fourier transform, verify what the right scale is. so that's fun. You have like this nice, it's actually very nice to know this because you can then construct interesting signals in time that use Gaussian, we say Gaussian because if this was a probability, the density function would be the Gaussian distribution, normalize the probability. But this signal, you can then construct interesting examples where it's easy to understand what's happening in the frequency domain because the frequency domain. Here's another one. So if that's scale, then it's not. But what that means is you could always pick the appropriate. So it wouldn't be. Let's say that the Fourier transform is f over. Then it's not an eigenfunction. However, you could scale this e to the minus t squared over something just right, so that it's scaled the same way. Okay, so another one is this. This one's important for today's discussion. Infinitely extended, and let's say all type 1. Okay. This we call a delta train. Train of delta function. Now, if you take the Fourier transform of this, then voila, you get the same thing. However, it's now 1 over t, 2 over t. So you can think of that as define 1 over t to be some frequency, f naught, then it's f naught, 2 f naught, 3 f naught, and so forth. Minus 1 over t, minus 2 over t. However, the scaling is not 1 anymore. It's actually, I think this is correct, and we'll check in a moment, 1 over t. So it's still constant, it was just scaled. So you get the same thing back, however it's scaled, and of course, you wouldn't technically call this an eigenfunction if you didn't match up. T equals 1, then it's negative. So that's fun. Here's another Fourier transform pair with the same frequency time. Now, actually, you can come up with infinite many of these. This, but these are probably the two most famous, most referred to. This one especially because it's relevant to the same thing, and this one because of other reasons. But we could invent our own. Here's an example of one. I'll do right here. I'm going to graph something. Okay, here's the axis. This thing, actually, when you do the Fourier transform, it's the same thing. Exactly the same thing if I do it right. Okay. How did I come up with this? So this is just C of T plus rect of T that I've drawn here. Right. Okay. Like that. Okay. All right. So let's think about this one. First of all, how can I define this? I mean, with the others, you could apply some integral and show that they're a Fourier transform pair. How do I do that with this? Of course, with delta functions, you always need some sort of trick. Maybe you'll show it in one direction, not the other. Usually, the trick to show that the Fourier transform of something has a delta function is you use the inverse. You always use the integral that's going to integrate over a delta function. However, we've got delta functions on both sides. So And we have an infinite number of these things, and that's going to get a little tricky. Here's the trick we're going to use to show that this is true. Okay, we're going to use, there's two ways to do it. So let's do it with the Fourier series. Okay, first way, proof number one. Fourier series. Now, this is periodic. So let's calculate the Fourier series coefficient. What is the period of this thing? P. Okay, let me give it a name so I can write it over there. Let's call this thing. Okay, so x of t has period T. And then we have AK equals the integral over any period. I don't want the edge of my integral to land on the delta function. That's going to be weird. So I can do any period I want. I'll integrate from negative t over 2 to t over 2. So integral from negative t over 2. I have a 1 over t here. And that's a t over 2. And it's my x of t e to the minus I 2 pi k over t dt. Okay, but fortunately, this is a very simple signal in that interval, right? So that's going to equal the integral, let's just say from negative t over 2, t over 2, 1 over 3. This is going to be a delta at time 0. Right? Delta of t e to the minus I 2 pi k over 2. Shifting property, what's that going to result in? What? It's 1. The integral here is just going to be plug in t equals 0 up here. That's just 1. However, we have this 1 over t, so it's actually 1 over t from that scaling up front. Okay? For all k. It's constant. All right. Now, let's convert that to a Fourier transform. Yeah, what? No, I'm not integrating 1 because the shifting property uses a delta function. It removes the integral. Yeah. So it's just a constant, 1 over t. And now all I do is I say, okay, therefore, x of f equals, we have a rule. We said how to take a Fourier series and turn it into a Fourier transform. It's going to be the sum k equals negative infinity of this thing, 1 over t, times delta of f minus k f naught, which was over k over t. K over t. Okay, and so this is exactly what I've drawn here. So we verified this is the Fourier transform. Now, I could equally well have proven this using a different approach. What I was going to do it, but there's not a lot of time, so I'll skip the second proof. But maybe I can ask for someone to figure out what the other approach would have been. That doesn't. So here we had the Fourier series. We went through the Fourier series and showed, and then used the conversion from the Fourier series to the Fourier transform. What else have we talked about today besides that? So we talked about representing a Fourier series as a Fourier transform. We also talked about representing discrete time signal as continuous time and vice versa. So we could have done this. We could have said, let me represent this as a discrete time signal. Okay, so we represent it as a discrete time signal. It's just a constant. And then we say, what is the Fourier transform of a constant? Well, we know that's a delta function. Of course, because it's discrete time, it has to be periodic. So we get a delta function of 0 and at periods of 1. Okay. And then all you have to do is rescale. because we have a relationship between the discrete time Fourier transform and the continuous time Fourier transform, and you get the same thing. Okay, so let's take our 2-minute break. Instead, you could say, well, forget the Fourier series. Just do the Fourier transform. Just take our initial XT and instead with the period t. Would be a constant. If you represent that with yes. So what's the Fourier? Okay. Now, time is actually periodic. So delta 0, but also a periodic extension, but it's discrete time periodic. Right? Yes. So it's a training delta with interval 1. And then you have to say, well, but for example, I have to rescale the frequency. That was so if you the continuous one is the time when scaled by well, this lecture. Go right here. So that's what gets us from a delta train period 1 to this delta train. Yes, exactly. That's why you get that. So. Okay, let's move on. So now we're going to get to it. We're going to get to the sampling. Okay. So here is our idea of sampling. In continuous time, you can think of sampling as the following. Let's say sample frequency we'll call f sub s. Okay. We have some continuous time signal. And now think of it in the following way. We are multiplying it with a train of delta functions. Okay. What would happen if I do that? I'm going to multiply by on the screen by the following. That's supposed to be uniformly spaced. So here's the x. Okay, so we have our x of t. We have a delta train. And this interval here is going to be 1 over fs. Okay, and what's the result of this? Well, for all purposes, at least under the integral, shifting property says that this is going to be equivalent, at least when it we're going to use this equivalence of the following, that f of t delta of t minus something else, tau. We're going to say that equals f of tau. The reason we say that, this is a common simplification, is because if there was an integral here, then these would be equal. Okay? If there was an integral, then this would just be f evaluated at tau. So it's an integral with respect to t. And if you integrate this with respect to t, hold on. Oh, this should still be a delta. Delta of. Okay. And if you integrate this with respect to t as well, you also get f tau. So shifting property basically says you can whenever you're multiplied by a delta function, you can replace this by just the value where that delta function is. Okay. So what that means is if you think about, you have this train of delta functions and you have your signal and you multiply them, the result is going to be just following. Multiplication of these two, and you're going to get something like this. Let me dotted line draw my signal again. You're going to get this. Okay. This makes sense why I'm saying that the product of these two things is that. Any questions about it? Okay. And then now we see that the result of this multiplication, at least if you converted this to a discrete time signal, that would be that's exactly what we meant by sampling. Okay. So the sampling we introduced at the beginning of the lecture is exactly the same as doing a multiplication of the train of delta functions. And this is the continuous time version of that discrete time signal. Yeah.
So, all these deltas and multiplications, they're all equally high for
Yes. Yes, exactly. So they have different intervals, but they're still this weird function. No, these by themselves don't. But what we wanted here is just to represent sampling. And if you think about it, our conversion that we defined between continuous time and discrete time take the discrete time signal and represent it in delta functions. Okay. So this is a valid. This is the continuous time representation of the sampling. But you're right. Like, it's not like this. The value of this function actually matches there, because the value of a delta function is worth that. Okay, it's the amplitude of that. Okay, so we can think of this as sampling. Now let's look at what happens to the frequency domain when we get the sampling. All right, so we'll call this thing. Let's call this down here x. I'm going to say sample that. I'm going to put a little fs, meaning it's sample. Okay, fs. Then what's going to happen in frequency? Let's first look at the frequency domain for just this, for just x by itself before it was sampled. Okay. I'm going to draw this kind of funny just to so that we can keep track of it. Let's say it looks like that. Okay, let's say that it had frequency content that after some frequency was 0. Okay, our original signal. So let's call this thing here F. I'll put a BW for bandwidth. That means suppose our signal had some sort of bandwidth, meaning that above those frequencies, there were no more, the Fourier transform was 0. Then what is going to be x, the sampled version of f? What's this going to look like? Any ideas how I can figure this out? I have a multiplication rule, right? So I know that multiplication in time is convolution. What am I convolving with? I'm convolving with this green thing. Fourier transform of a delta train? It's a delta train. So what I have here is I have my XF. I also have a delta train, let's say, like this, or let's say that it's like this. And what's the width of this delta train? That's going to be what is this value up here? It actually depends on my sample frequency. So this is 1 over Fs. So this is Fs. And this is 2Fs. And minus Fs. Okay, and the height also is just going to be Fs. Right? Yeah. Okay. So now, so what does that mean? I'm convolving these two things. So convolution just means I end up with this. I end up with this one here. And I repeat it here and here. Okay, do you see that now that green is the result of, is the Fourier transform of the sampled version. All right. Now, suppose now I've drawn this as if f bandwidth is, I've drawn it as if that is less than 2 times fs. Okay, that's what my drawing looks like. If the bandwidth is smaller than 2 times the sample frequency, I don't get overlap. Right. However, if f bandwidth was greater than 2 times fs, then I would be looking at a different thing. I would have my I would have these things overlapping. Do you see why that's the case? Okay, because my delta train would be too close together that they'd overlap. Right? So what that means is, can anyone think of a way where I can recover this Fourier transform from this one? You said circular convolution of what? Okay, I heard another comment. What? Yes, what if we low-pass filter this thing? Let's say we apply an ideal low-pass filter. And just to get the amplitude right, let's make the height of this thing a 1 over Fs. Because we had those Fs there. So let's say that the width, let's make it Fs over 2 here. We low-pass filter. We have the cutoff frequency be the sampling frequency over 2. And assuming that the bandwidth was less than double the sampling frequency, this should recover our signal exactly. Okay? Pretty cool that we sampled it, and yet we get back the entire thing. Now in the time domain, in the last minute here, let's look at what is a low-pass filter? A low-pass filter, ideal low-pass filter, is convolution with a sink. So low-pass filter is convolution with sink. And when you put in the exact stuff we have there, would be sink of t times fs. It would be sink of t times fs. And then we put in this thing here, it would be 1 over fs up front. Okay? So if we convolve with that in time from our sampled version, assuming that we were within the bandwidth, that we didn't have a bandwidth that was too large for our sample frequency, then we get back exactly the signal itself. Now, that means something very cool. Let me draw these samples. We talked about a couple of methods of connecting samples to try to get back the original signal. We talked about connecting them with lines, just putting straight boxes. Both of those two methods could be interpreted as a convolution. One of them is a convolution with a rect, one's a convolution with a triangle function. And next time I'll comment on this a little bit more. But here what we're saying is convolve with the sinc function. And we match the sinc up exactly so it's the following. The sinc looks like this. So sinc has zeros exactly at the intervals where the other samples are. So the sinc is going to be the sum, the convolution of sinc is the sum of a sinc at each one of these delta functions, right? So I'm drawing a sinc centered at each of the delta functions. And the cool thing is that when you add these things up, you add all these functions together, you'll get back your original signal. Okay, so what I've done is I've drawn a sinc scaled by the sample value. So this is sinc interpolation, and that's how you recover the signal exactly. We're done for today.